Hello everyone, let's look at this rational function integral. So we have a rational function here, and usually the way that we integrate this kind of function is that we are going to use partial fraction decomposition. So we are going to decompose this rational function into the sum of fractions. And then because those fractions become simpler. So what we're going to do is that we should be able to integrate those fractions directly. So now what we are going to do is that we are going to first factor the denominator, right? Because this is not in the factor form. So first we are starting the problem by just copying down this here. So 5x squared plus ax plus 20. And then okay, so now let's work on the denominator here. So for the denominator, we are going to factor out the x. Okay, so let's factor out the x. So if we factor out the x, then we are going to be getting x squared plus 2x plus 5. Okay, so now we actually get a product of two expressions here. One is the linear expression, it's just an x. The other expression is a quadratic expression, that's x squared plus 2x plus 5. Now, how do we know that whether we should continue factoring this quadratic into linear factors, or whether we can or cannot, right? So how do we do that? What we can do is that we can use the discriminant. So the b squared minus 4ac for this quadratic expression, and see if we are actually getting any real solutions for if we are setting this equal to 0 and solve the equation. So let's just do the scratch work on the side. So what we're doing is that we are going to just do that here, x squared plus 2x plus 5. And so you can see that the a is equal to 1, b and b is equal to 2, and then c is equal to 5, right? So what we're going to do is that if we use the b squared minus 4ac, right, b squared minus 4ac, and then try to compute this discriminant, we are getting b squared, so we get 2 squared, okay, minus 4 times a times c. And so you can see that that's just equal to 4 minus 20. And so you know that's less than 0. So that means we are not going to be able to factor this expression further over the set of real numbers. Unless you factor it over the set of complex numbers, then you can. But right now, we are not going to do that. And so that means this is an irreducible quadratic expression. So the way that we are writing down the form of the partial fraction decomposition is that we are going to write it like this. For the linear factor x, we are going to just put a constant at the top. And so we just get an x at the bottom, okay? And then for the non-reducible quadratic, right? Then, so let's just put the denominator first. What do we put at the top? We are going to put a linear expression at the top. So bx plus c. This is the general form for a linear expression. Okay. So now we are going to do what? We're going to multiply everything by the LCD for the whole equation so that we can get rid of the denominators. And then we only need to worry about dealing with the numerators. Okay. So what is the LCD here? The LCD is going to be x times x squared plus 2x plus 5. Okay, it's actually just those two factors. So what are we going to do now? We are going to multiply both sides of the equation by this LCD. So as you can see for the left side, for the original function, if you multiply by the LCD, you are going to be able to cancel the x. And then you're also going to be canceling the x squared plus 2x plus 5. So we are getting just the 5x squared plus ax and then plus 20. Okay, so far so good. Now, what about the right-hand side? For the right-hand side, we have x here, and that's another x. So if we multiply this fraction, a over x, by this LCD here, then the x's will get canceled. And then we are going to just be getting an a here, and then times whatever that's left that didn't get canceled. So we are going to be multiplying the a by this expression, which is the x squared plus 2x and then plus 5 plus, Okay, so now what about the second fraction here? The quadratic will get cancelled. X squared plus 2x plus 5 will get cancelled. So we are just left with the bx plus c times that x. So we get bx plus c. Yeah, don't forget to put in a pair of parentheses. Okay, and then also dx. So right now, what we're going to do is that we are going to be we're going to be expanding this and then try to match the coefficients on both sides, right? Because now we are claiming that the two polynomials are equal, so all we need to do is to write both polynomials in descending order and then try to match their coefficients. So let's do that. So here we are going to be getting 5x squared plus ax plus 20 and then equals. Okay, so now distribute the a. So we are going to be getting ax squared plus 2ax plus 5a and then plus. Okay, continue. Here, distribute the x to the bx and the c. So we are going to get bx squared plus cx. Okay, so the next step is to just combine like terms on the right-hand side of the equation. So let's just group the like terms together. We have ax squared and then plus bx squared. And then also the linear term. Linear term, this term here has an x and that also has an x. So we have the other linear term, and then now you're left with just the constant term, so we don't need to do anything here. So let's just put that down. So we get 5x squared plus ax plus 20 is equal to, okay, so now the green quadratic terms, right? So we have the a plus b x squared, okay, plus, okay, so now the linear term 2a plus c times x. Okay, and then just the constant term, so 5a. Okay, so now that's good so far, right? Okay, so what we're going to do next is that we are going to match the coefficient and then set up a system of equations. So we are getting this and that, right? Matching with this side. So we have a plus b, because a plus b is the coefficient of the x squared term. So that's equal to the coefficient of the x squared term on the left side. So it's equal to 5. Okay, so now the linear term coefficients matching. So we have 2a and then plus c, right, is equal to 8. So we get 2a plus c equals 8. And then lastly, the constant terms matching together. 5a is equal to 20. And so do you see what's going on here? The answers are really easy to find because there is only one variable for this equation. And so all you need to do is to solve for a here. So that tells you that a is equal to 4, right? If you divide both sides by 5. And then now once you figure out a, you can plug it back into the first one and the second one, and then you can figure out b and c. So if you plug it back into the first one, then we have 4, okay, we have 4 plus b is equal to 5. And so b is equal to 1. And then now plug into the second equation, then we are going to get 2 times 4, right? That's 8 plus c is equal to 8. So it just happens that c is equal to 0. Okay, so now we found the ABCs. So we are ready to go back to the original integral, okay? And then we can start rewriting the original integral as the sum of fractions, and then we can integrate each fraction. Okay, so let's do that. So we have the original integral, which is 5x squared plus ax, and then plus 20. And then, yeah, I'm just copying that here, but you don't have to, right? So I'm just making it look nice, but you don't really have to copy down the original integral. Okay, so the first integral that you're getting is that, let's go back up and see what's going on. We have one of the fractions is that it's a over x, and so we're going to put the 4 and then over the x. So that's our first fraction, first integral. 4 over x dx. That's good. And then next one is the integral. We have bx plus c. C is 0, so bx, which is just 1x, so x at the top. And then the c is that irreducible quadratics, right? X squared plus 2x plus 5. And then the dx. So now that's that. And so we don't need the above information anymore. We are ready to actually start doing the integration, right? So let's do the integration right now. This one is easy. We can just integrate directly. Then you may say, what about this one? This one, it would be a good idea to complete the score first and see what happens. Okay, so let's do that. What I'm going to do is that we are going to just integrate this one directly, right? So we are going to do 4 ln of absolute value of x. Okay, so now what about this thing right here? If we complete the square, then it's going to look like this, x. So what are we doing? We have x squared plus 2x. And then if you complete the square, you take this, the coefficient of the linear term, you divide by 2, so you get 1, and then you square it, so that's still 1. So you're going to be adding 1 right here. Okay, so just add the 1. And then you plus the 5, right? There is still the 5 there, but you cannot really change the problem. So I think I need to draw a longer fraction line here. So what do we need to do to balance it? When we're adding the extra 1 here, we got to subtract it back. Okay, so let's subtract the 1 back so that we are not changing the problem now. Okay, so continue. We have 4 ln of absolute value of x, and then plus the integral of x at the top. And then at the bottom, we are completing the square. What's happening here is that we are going to be putting this into a perfect square, this expression right here. Okay, this expression. Then that actually turns into what? X plus 1 square. Okay, and then what about the other stuff? The 5 minus the 1, then we are going to get positive 4. Okay, so now we have this expression. Then you may say, what do we do? What do we need to do next, right? What do we need to do next? It would actually be a good idea to do a use up so that we can do the integration on this one. So let's just do the use up on the side, right? So let's do that. We are going to be having let u be x plus 1, okay? So du is going to be dx. But you know that we also need to replace this x, right? So you need to solve for x right here. So if you solve for x, then x is going to be u minus 1. So that's something to keep in mind. So continuing with the problem, right? So we get 4 ln of absolute value x plus, okay, so the integration becomes, right? The integral becomes, we have the u minus 1 at the top, and then at the bottom, we are going to be getting, what is that? We are going to be getting u, right? Because the x plus 1 is being replaced. So u, then square, and then plus 4. And then du, right? dx is equal to du, so we replace that. And then it would actually be a good idea to split this integral into two, right? So if you do that on the side, right, this integral actually, this integral, as you can see here, it actually is what? U over u squared plus 4 du minus integral of 1 over u squared plus 4 and du. You see what's going on here? Why do we need to split up the two integrals? Because this one, it's to use the u sub, and that one, yeah, so we got to do another u sub. And then that one is actually just the inverse tangent, right? So that's what we need to do right now. Okay, so let's continue. Let's continue. Okay, so we are going to be getting 4ln of x. Okay, so now what do we do with the u sub? If we are doing the u sub, then we are going to be let's just use another substitution right here, which is what? Which is, let w be u squared plus 4. So dw is equal to 2u du. And then we don't really have a 2 here, right? So all we need to do is to get the 2 on the other side. So we are going to get 2 1/2 dw. We're going to use u again because there is a variable conflict, right? So I'm going to use w. And then we have 1/2. And then that's equal to u du. And u du is actually just being replaced by 1/2 w. Okay? And then the bottom is replaced by w. So the integral actually becomes integral, okay? And then u du is replaced by 1/2 dw, so we are going to be getting 1/2 and then dw over what? Over just the w. And then right now, this one, we can actually integrate that easily. So if we are integrating this one, then we are actually going to be getting, let me use a different color here. So for this one, right? For this one is going to be become 1/2 tangent inverse, right? There is a formula you can use, x over 2. Okay, so that's actually just giving you that. And in this case, it's not x, it should be u, right? It should be u. So that's something to keep in mind. So we are going to be getting minus, right? And then all that stuff. So we have 1/2 tangent inverse of u minus 2. Okay. This one is actually really easy to integrate. So we are going to just integrate that immediately. So we are going to be getting 4ln of absolute value of x plus 1/2 ln of w, okay? And then minus 1/2 tangent inverse of, what is u equal to? U is actually equal to x plus 1, so we are going to put it back as x plus 1 right here. And then plus the constant k. Well, the w, we also need to switch it back. So it's going to be u squared plus 4, but then u is also x plus 1. So if we switch everything back to x, then we have 4 ln of absolute value of x. Okay, and then plus 1/2 ln of x plus 1 quantity square, and then plus 4, right? Because if we replace the w, then it's u squared plus 4. And then, so it's something squared plus 4. What is that something? That u is x plus 1, so I put the x plus 1 back in. And then minus 1/2. And then tangent inverse of x plus 1 over 2. And then plus k. And then we're finished with this problem. Okay, I cannot be using the C here for the constant integration because we already have a C that's in the that's being used as the unknown for the constant, right? When we're doing partial fraction decomposition. So that's our final answer, right? So this example shows you a lot of different things. There is something that you can integrate directly. Once you split up the integral, you are going to run into a u-sub situation. You can also run into a situation with the arctangent, right, when you integrate. So those are the things that you have. Okay, so that's it for this problem. If you like this video, please give me a like, subscribe my channel, and share my videos to others. It will give me support to make more videos. If you have questions or have a topic that you want me to talk about, please leave me a comment. Thank you for watching this video. I will see you next